Recording in progress.
Hey, my name is Dave Perry. Here's my presentation on Huffman code compression. And so let me get started. Yes, so here's my presentation on it. So I really enjoyed learning about the Huffman code compression during this semester, and so I wanted to make my presentation on it. The purpose of a Huffman code tree is to find the optimal amount of bits to reduce encoding while you're encoding a string. And so normally each character in a string would be 2 hexadecimal codes or 8 bits total. And so, yeah, just using the Huffman code compression greatly helps reduce memory usage and helps with efficiency that way. Um, and so normally when you are encoding something, like I said, it would be 8 bits each. And so the text string that I'm doing, I have completed CSC 381, let's go. That would be 328 bits if each one was 8 long. And so that's quite a bit of bits. Anyway, and so the first step that you need to do is profiling. And what that means is in code, you have a dictionary and you just go through the string and count every time that these letters are used in the code. And so, for example, let's see, sorry. Um, so the I, there's only one I in there, so the profile is 1. But then the spaces, there's 6 of those. The O's, there's 8 of them. And so, yeah, it just tells you how often these different characters show up in the text. And so, yes, to build the tree, in the code we used a priority queue, which helped with just keeping the priority queue sorted the letters depending on their count values or how often they appear in the string. And so this would be how I organized it. The program did it a little bit different, so this isn't going to be completely accurate to the final output of the algorithm, but this is just a hand done one right here. And so, yeah, this is just all of the letters in order, with O being the last, I being the first. You dequeue the first 2 letters, and then you combine those together into a node. And each of these are already a node, just with no branches. But this one, you create a new node, append the leaves of I and H to it, and then you insert it back into the tree in order. And so all of these letters, they're all equal to 1, or all of these characters, until I and H is now equal to 2, C is also 2, L is 2, T is 2, and then so on. You continue this process, combine all of those. Now, this single one is by itself. These are all the same as these ones. Combine it again, just keeping the order, combine it again, and yeah, my artistic abilities start getting a little bit sloppy, but you can just see that each iteration of going through the queue, it gets bigger and bigger and bigger until eventually you come out with a big tree like this that has the most used values at the very front. And so for this one, if every time you go, and the next step as well is after you build the tree, you encode the tree. And so each time you go left on the tree, it's a 0. Each time you go right, it's a 1. And this just makes sure that no prefixes match each other. So like 0, 1, 1, you're never going to see that again in the tree in without something before it. It's, yeah, each prefix is unique. And so to get to O, it would be 0, 1, 1. To get to, I use an underscore, but this is the space 0, 1, 0. And H's that aren't used as often, it would be 0, 0, 1, 1, 1, 1. So that's how you build the tree as well as how you map it. And yeah, so that's how that part works. Once you encode it, once the algorithm encoded it, I got these values, which are a little bit different and a little bit more optimized, like this 0, 0. The O is 0, 0 instead of 3 bits like I showed. The space is still 3. The E is 3. The space is 3. So just a little bit better than my hand drawn. I probably made a few mistakes, but that's the output of the actual algorithm. And then with all of these codes, you can now build the encoded string. So like that yellow highlighter is equal to the I, right? Yeah. So the I right here and then goes on. That's the green is the space, H, da, da, and then decoded, it all correlates there. So yeah, that's how you do that. And the performance of it is for both of them, um, the worst, best, and average. So big O, theta, and omega are all M or N, sorry, theta, omega, big O, omega, theta in order is all M with M being every letter in the text, and the decoding is also just N, but N is the numbers of bits that is being decoded. So yeah, so after this, the original length again was 328. With this Huffman code compression, it was 156. And yeah, it's just a great way to cut down your strings. And so now I can go through the code with this. I wrote some tests to make sure this all works, and I did test all of them. Let's see. So yeah, so here's how you profile it, just making sure all these values are the right ones. I checked a few of the branches in the tree, not as much as we did in the class, but that was a lot of work. Created the encodings, make sure they're all correct. Make the encode and the decode. So perfect. And so then the actual code, just to run through it, we create a node class, define the letter, the counts, and the branches coming off of the node. Then we create the profile, which is a dictionary. We just go through each letter in the text. If that letter has not been seen before, just kidding. So if the letter has already been seen, we add one to it. If the letter has not been seen, then we create a new dictionary element and put it as one, since we just barely saw it for the first time. And yeah, that just goes through to create all the profilings. To build a tree, we use that priority queue that I was talking about earlier. We go through each letter within the profile dictionary. And then, yeah, this is just assigning all of the letters in the dictionary to different nodes, and then we're inserting it. So then we're inserting it into the tree depending on node.count. So that's how we keep it organized. And then we dequeue the smallest count values. We make a new node called Z. We make that Z node count equal to the counts of the two dequeued values added to each other, the sum of those two. We make Z left and right to the two node values, and then insert that. And so eventually, like I showed before, the trees get bigger and bigger. So these X and Y values, they're not just a single letter value, they're a whole mini tree that is being combined. And then, of course, once the queue is only one and we dequeue it, that's the whole Huffman tree completed. So we just return that dequeued tree. And then, yeah, to create the mappings, we just create a map dictionary, and then we run this helper function. These are just base case. If the node is null, that just means that we have an empty tree being passed through. Let's see. And so, so if both the left and right nodes are null, that means that we have now reached a leaf. So that means that we can know that, we've reached a leaf. And so if the code length is 0, then we return 1, because that means there's only one thing inside of the tree. If we haven't, because the code length at first is just an empty string. That's passed right here, just an empty string. And so if it's 0, once we get to that point, we just know that there's a single item and we assign it to 1. Or if it's not, then we set whatever the result is right now that we've been building over time to that code. And we build the code in this part right here. We go to left and add 0. We go to right and add 1, just like I was showing before. Depending which direction you go, you add a 0, 1. That builds the code that will be put down right here. In code, you just go through the letters in your text and you run it through that map that you just made. and you're going to keep appending that to a big long string and then decoding it. Similar thing. You start at the top of the tree. The result right now is 0. You go through each node until you find another leaf, and then you add the result, that letter to the result, and then return to the back to the top of the tree. And the result is going to be from the code that's been building up. It's going to tell you which letter that is, which will be added to the result. And so, yep, that's how a Huffman tree works. That's my presentation. Hope you all enjoyed it and appreciate your time.